let's look at some examples involving total distance. In this first example, a fly moves with velocity sine of t, where that's measured in centimeters per second. First of all, suppose we're asked that after 5 pi over 2 seconds, how much has its position changed? So what you want to think about there is that's another way of asking about the displacement of the fly. So that means that we can evaluate over the time interval 0 to 5 pi over 2 the integral of just the velocity. So the antiderivative of sine here is minus cosine, and we're evaluating that from 0 to 5 pi over 2. And this gives us minus cosine 5 pi over 2 minus a negative, so plus cosine of 0. And if you recall that cosine of 5 pi over 2 is 0, this is going to give us 1. And again, with this context, I know that I can put the units centimeter on this. So same time interval after 5 pi over 2 seconds, but how far has it traveled? Now this is instead asking us about the total distance. So we need to integrate, again, over the same time interval, but the absolute value of the velocity function. And as we saw in the previous video, that very much means that I need to focus on where sine is positive and negative. So we can think about the sine graph here, and sine passes through the origin, and then we know that it comes back down at pi, it comes back up at 2 pi, and then it's going to basically come back up to about here at 5 pi over 2. So we need to pay attention to the portion where it's negative, which is between pi and 2 pi over 2. Excuse me, 2 pi. So the absolute value of sine would flip this part upward. So when I'm integrating, what I really want to look at is the integral from 0 to pi of just regular sine, and then plus the integral from pi to 2 pi of minus sine. Oops. And then from 2 pi to 5 pi over 2, we go back to just regular sine of t. So that's how we deal with the absolute value. Now, actually going through this, the antiderivative of positive sine is negative cosine, and the antiderivative of negative sine is positive cosine. So we just need to account for all of these points of evaluation here. Let me make sure that this graph is kind of off to the side. And so going through and actually evaluating this, we're going to get negative, so in this first part here, negative 1, because cosine of pi is negative 1. And then we get minus a negative, so plus the cosine of 0, which is 1. And this second part, cosine of 2 pi is 1, and we're subtracting cosine of pi, so subtracting minus 1. So notice we get 2, and we get 2. And in this last part, we get negative cosine of 5 pi over 2, which is 0, minus a negative, so plus the cosine of 2 pi, which is 1. So the total distance is here 5, and again, I still have the same units of centimeters. So we can see how to compare that to our displacement from the first part of the example. Okay, in my second example that I want to cover, let's put this here, we're going to assume that we have the velocity of a particle in centimeters per second is t squared minus 10t plus 24. And much like the second part of the previous example, I want to find the total distance traveled by the particle over a particular time interval. So for this one, it's not as obvious to me as with, say, the sine function, where this is positive or negative. So what we have to do is a little bit of analysis on that first. So v of t is t squared minus 10t plus 24. And I can factor that into t minus 6 times t minus 4. what's useful about this is now I can see where the velocity is positive and where it's negative. You can see that you have these critical points at 6 and 4, and we kind of want to analyze what's happening to the left of 4, between 4 and 6, and to the right of 6. So when we look at this, you can think about plugging in a representative point. So if you were to plug in, for instance, 0, you would get a negative times a negative, it would be positive. If you plug in 5, that product's going to be negative. And if I plug in something like 8, the product's going to be positive. So we see that v of t is greater than 0 when either t is less than 4 or when t is greater than 6. And we see that v of t is smaller than 0 when t is between 4 and 6. So without even having the graph of that, now I have enough information to be able to integrate the absolute value. So from 0 to 10 is what we're hoping to find the integral of the absolute value of this velocity function. Now, from the analysis above, I know that I can integrate on the interval from 0 to 4 just the given velocity function. And then I can integrate the negative of that. So from 4 to 6, so this would be minus t squared plus 10t minus 24. And I'm running out of room. And then I'll put it here. From 6 to 10, I go back to the positive version of v of t. So this is how we account for that absolute value. So now going through and evaluating this, we just have to be careful. I end up with t cubed over 3 minus 5t squared plus 24t. We're evaluating that from 0 to 4. And then I have, essentially, we're going to have minus t cubed over 3. Oops, this is going to be minus 5t squared plus 24t. And that's from 4 to 6. And then finally, t cubed over 3 minus 5t squared plus 24t from 6 to 10. Now, in the interest of time here, we can plug in these values, and what you're going to find is we're going to get 112 over 3 from this first part. We're going to get what ends up being positive here, 4/3 from this part, and another 112 over 3. And so all together, we can add that up. That's 224 plus 4, so 228 over 3. And again, my units are centimeters. So the main thing I want to get across from this example is you don't really have to necessarily graph the velocity function when you're trying to find the integral of the absolute value. But we can lean back on our knowledge from Calc 1 to be able to determine where is the where is the velocity going to be positive and where is it going to be negative? And that's really what we need to know in order to be able to appropriately break up our integral to deal with the absolute value.